So again, take a minute, find out how fast the box will be traveling after it's traversed the 5 meters. Do so by using work and the work energy theorem. Because I want to get to some of the stuff that's a little different than this. Let's just kind of walk through. How many forces act on the box? 4. But how many do work on the box? 2. So can I just like not worry about the weight and the normal force? Because they don't do work on the box. In this particular problem, the box travels sideways, but those forces are up and down, so they can't do work on the box because they are not in the direction of motion. Now, I don't want to say that normal forces can't do work ever, but they can't do work here because the box isn't going up or down, and the normal force is up. So remember, the only forces that can do work are the parts of the forces that are in the direction of motion. So right now, the work done by the normal force is 0, and the work done by gravity is 0 because the box never moves up or down. But the work done by the applied force, that 20 Newton force, that's just going to be 20 times 5 times the cosine of 25 degrees, which I believe came out to be like 90-something, right? 90.7? And the unit here is a joule. Any questions where I got that from? All right. The work done by friction, well, it's 6 newtons times 5 times the cosine of 180 degrees. Anything weird there? Anybody need me to explain any of that? All right, you say that, but when you have that quiz later this week, I don't want to hear any complaining. This is going to be negative 30 joules. So we've talked about the work done by each force. Any questions about it? We add it up. Net work done. Looks like 60.7 joules. Now, this is big. Net work equals the change in kinetic energy. That's important to know. If the amount of work done is positive, the object's going to be going faster. If the amount of work done is negative, it's going to be slower, but only if there's a net work done. And change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. So for this example, I have 60.7 joules of work done on the box, so the box had to increase its energy by 60.7 joules. Bless you. Well, that's got to be 1/2 mass of the box times the final velocity squared minus 1/2 times the mass of the box times the initial velocity squared. If the box started from rest, then this is just how much kinetic energy the box has after it was pushed. The box had a mass of 10 kilograms, so that leaves the final velocity 3.5 meters per second. Any questions about that? Is that relatively okay? Now, this is not the only way to do this problem. If you wanted to, you could have drawn a free body diagram, put together all the forces that are acting on the object, apply a coordinate system, using that coordinate system, find how much the acceleration was in the x direction. Looking at this, I'd have a component of the force this way. That would be 20 cosine 25. And a component this way, that would be 20 sine 25. So my net force in the x direction would be 20 cosine 25 minus 6 equals ma. Right? I mean, this is the other way we would have done the problem. And from there, we would have gotten an acceleration. We could have said, okay, there's an initial velocity, final velocity, displacement and time, and we could have done a motion equation. It would have done the exact same amount of work, would have been the same problem. Here's the difference. This is what you should write down in your notes. I gave you the frictional force. You were given how big the frictional force is. If you had to figure out the frictional force, you probably would have had to use forces anyways. I mean, if I didn't give you the frictional force and I said the coefficient of friction was 0.3, well, you probably would have had to do all the work that we did last unit because you would have had to have found the normal force so you can plug it in here to find the frictional force. To understand the reason this problem is pretty easy using energy is because you were given the size of the frictional force. But if you're not, you might have to do all the forces stuff. I'm saying this because the problem is not going to say, when you take the exam, it's not going to say this is a work energy problem. Use that. You'll have to discriminate and determine which thing is going to be the best way to attack the problem. I will say there are things that you can look at to understand if you want to know if the work is changing. If the object's velocity changed, work was done. You may not know by what, but if the object's velocity changed, work was done. That's important to know. All right. I want to move on to something different, okay? I want to add something to this conversation. And this might be difficult to understand, so I'm going to do my best. And I usually have difficulty explaining this the first time. So let's say this is the ground. No trouble? Okay, thank you. Just lay them on my desk. That'd be great. Perfect. So imagine I have a box, and there's a shelf over here. And I want to take the box, lift it up, and put it on the shelf. Okay? Everybody follow what I'm saying? It's pretty straightforward. So I want to do it just as you saw me do it. I want to lift the box straight up. Then when I get there, I want to slide the box sideways. Does that make sense? Okay. Now, when I lift the box, I'm going to use an upward force on the box. So, and I'm not going to push too hard. I just want to lift the box at constant velocity and then move the box over. Everybody understand? Okay. Let's say that the box has a mass of, I don't know, just 5 kilograms. I need just to have a number. And let's say the shelf is not particularly tall, but taller than me, so we'll say 2 meters tall. Okay? As I lift the box, how many forces are acting on the box? Can you name a force that's acting on the box?
Gravity.
Gravity for sure. So there's gravity acting on the box. And what else?
The applied force, right?
Yeah. Normal force, applied force, something. Whatever I gave to the box. Fair enough? That makes perfect sense, I hope. So as the box is moving upwards, I can think of 2 forces acting on the box. There's gravity acting downwards on the box, mg, 50 newtons. And there's me acting upwards on the box. If I want the box to rise at a constant velocity, how much force do I have to apply to the box to get that to happen? No, not more than 50. I agree that it would take more than 50 to get the box started. But once the box is moving, if I just want to keep it moving at a constant velocity, I only have to apply 50 newtons. If it's moving at a constant velocity, net force is 0. I'm trying to be very careful about the way I phrase this, but none of this should be a surprise. Do I need to say any of that over again? Are we sure? I don't want you to screw your test up. Yeah.
Well, how are you finding work if the velocity is 0, or there's a constant velocity?
Well, I haven't made my point yet, so give me a few seconds, okay? So there's the work I do here in lifting the box. And there's the work gravity's doing here in acting on the box. So there's the work done by me, which is going to be what I applied, 50 newtons, right? And I applied that 50 newtons over a distance of 2 meters. And I pushed upwards, and the box is going upwards. That all good? All right. There's the work done by gravity. And that's going to be, well, the box weighs 50 newtons. And the box moved upwards 2 meters. So gravity did work on the box. But it's negative. Because the box went up, but gravity is pulling down the whole time. So I did 100 joules of work on the box. Right, 2 times 50. But gravity did negative 100 joules on the box. We worked against gravity. That's a net work of 0, which is why the box's velocity didn't change. The box changed location, but its velocity didn't change. Now, that means I got the box up to here, and then I did a little bit of work just sliding the box over, right? I don't know how much. Because, I mean, if I'm actually lifting the box, I would probably lift it pretty close to the shelf. I would imagine that lifting it over wouldn't be very much work. Would you guys agree? Now, gravity did no work when I slid the box over. If you don't know why, write it down. I'll tell you why. Gravity did no work as I slid the box over because I moved the box sideways and gravity was still acting downwards. So I might have done a little bit of work to slide the box over. But gravity didn't do any because gravity acted downwards and I slid the box sideways. Now, this next part might be hard for you to understand, but I need you to make like a kind of a mental image of it. Maybe I am weak and shaky. Okay, maybe. And when I lifted the box, I was all over the place, lifting the box upwards. Does everybody understand? I might have done more work because I was not able to move the box in a straight line. Do you understand that gravity did no more work? That it would still be just 100 joules? Because even if I lifted the box, like, say, sideways like this, gravity was acting down the whole time. So the only part that mattered was the part that equated to me lifting it 2 meters. And I want to prove this to you. So to prove this to you, you have to do more math. So do you want it proven to you? Let's prove it. We're only talking about gravity for right now. So I'm going to make a ramp for me to do this with. And I'm going to move the box along the ramp. So I move the box this way along the ramp. Okay? Now, gravity acts downwards. So there's no difference. The force from gravity is still downwards. Does that make sense? I'm not talking about my force. I'm not talking about the work I did. I'm saying gravity acts downwards. Somebody give me what angle you want to use here, because I don't care.
30.
30? If this is 30 degrees and this is 2, how long is the ramp? Now, I'm not trying to trick you. You guys who are paying attention and are staying with me, stay with me a little bit longer. I want to find out how long the ramp is because I need that to figure out how much work was done. So this is the hypotenuse, or I'm sorry, this is the opposite side, this is the hypotenuse, so sine of 30 would equal 2 over the hypotenuse. This is going to give me the length of the ramp. I am expecting that you can do this because you passed triangle, right? We passed triangle months ago, so you can do triangle stuff. If I work this out, can you tell me what the length of the ramp is? I'll wait patiently, but sine of 30 is a half. So, yeah, 0.5 h equals 2. So the length of the ramp is 4 meters. Everybody okay with that? Everybody see it all right? So, I want to calculate the work done by gravity. The box moved 4 meters along the ramp. By the way, I need this angle right here, because it's the angle between the displacement and the force. Now that one I'm a little worried about. I don't know if you guys can find that one. Do you know what it is? Do you know how to find it? You should be able to, but maybe we'll focus on, say, this one. Do you know what this angle is? There's just a triangle there. Can you see the 30 degrees? What does this angle have to be if this one's 30 degrees? 60. Excellent. What does this angle have to be if this one is 60 and all of this is 180? So you guys do know how to find it. Are we all good so far? Did you find out how we got all that information? Okay. I want to find the work done by gravity along the ramp. The work done by gravity along the ramp. So it was a 50 Newton force. And it looks like we pushed for 4 meters. And it would be the cosine of 120 degrees. Can you do all that? Because that looks hard. Negative 100. It's the same. So, if you don't remember the question I asked, and you now want to put something incredibly important in your notes so that you will be able to remember this. Work done by gravity is path independent. Work done by gravity is path independent. So the fact that I use the ramp or the fact that I lift the box straight up to the top is the same, which is why that whole shaky route, path independent, it won't matter because gravity is down the whole time. The only part where work is being done by gravity is when the object changes height. That's huge. That's big. Put that in your notes. The only time when work is being done by gravity is if the object changes height. Well, it's not working out the way I wanted, so there we go. Get rid of that. Get rid of that. That. And I can erase the rest. Okay. Back to my shelf issue. Got my box, putting it on the shelf. Now, maybe I get the box up there and it's a little shaky and the box falls to the ground. The box falls and I don't catch it. Can you tell me how much work was done by gravity? Don't make this part hard, guys. It's still 100 joules, right? It fell 2 meters. It's the force of gravity is 50. The difference is that the work done by gravity is now positive because the box went downwards and the force of gravity was downwards. Does that make sense? But I didn't catch the box. So how much work was done by me? 0. So the total work done, the net work done on the box is 100 joules because it was from gravity. I know you're wondering where I'm going with this, but you understand that if the box had 100 joules of work done, then that would be the change in kinetic energy of the box, correct? You could figure out how fast the box is going by just setting the 100 joules equal to the change in kinetic energy. I don't need you to do that, but you see that we could do that, correct? Do you realize that if I had lifted the box to a lower shelf, the box would have less work done by gravity if it fell? It would be going slower. Or if I lifted it to a higher shelf, there'd be more work done by gravity if it fell. People recognize that idea, that there's something about the height of the object that would change how fast it was going if it fell. They also recognized that it didn't matter how the box got to that height, that once it got to the height, the work done by gravity was based just on the height of the box, not the path it took to get there. So, what we have decided to do because of this relationship is to define potential energy as the work done against a conservative force. We define potential energy as the work done against a conservative force. This is one of the most important things I'm going to talk about this week. We define potential energy as the work done against a conservative force. In fact, in this case, we're going to use some symbology, and you will not really care about this after today, but we say that potential energy equals minus the work done by a conservative force. This is the definition. So if you care about definitions, that's what you should write down. It is a definition for potential energy. We will define the potential energy as the work done against a conservative force. So, when I lifted the box against gravity, gravity did negative 100 joules of work, which means we say that the box gained 100 joules of potential energy. Listen, this is an aside. Whenever you lift a box, gravity's doing negative work on the box. But what we're saying is that the box has something now that it's been lifted higher. It has the potential to fall. We say that by lifting the box, we have given the box something. We're saying we've given it energy because we separated it from the earth. I lost 100 joules of energy to give that to the box, to get it up to the top of the shelf. And once it's at the top of the shelf, the box has gained potential energy. I know that sounds way complicated, but here's the deal. This is path independent, meaning if I build an interesting ramp and I put some cars on it with little wheels on it, and I use a chain to lift them to the top, you'll notice the angle that the train cars make as they go up to the top of the hill is changing all the time. But gravity acting on the train cars will always be straight down, correct? So work is being done against gravity to get the train cars to the top of the hill. As I said a minute ago, once there, it doesn't matter what path it took to get there. They will have gravitational potential energy. It's path independent. The chain gave the cars the energy, but once they're higher, once they're above where they started from, they have gravitational potential energy. You follow along so far? Now here's the big deal, the thing that is important. If there's no other forces acting on the system, then no work can be done on the system. Now this part's important. If there's no other forces acting but conservative forces, then the amount of energy in the system stays the same. If there's no other non-conservative forces acting, so I take away air resistance, I take away friction, the amount of energy in the system stays the same. So this part's going to be harder for you to understand, I think, in the beginning, but it's super, super simple. What it means is, as the cart falls, it's lower to the ground. Do you think it has more potential energy or less potential energy?
Less potential.
Less. It's closer to the ground, right? So it has some potential, but it's going to be less than the potential energy it had here. That energy had to go someplace. So in this case, gravity, being the only force acting, did positive work on the boxes, or on the train cars, and gave them kinetic energy. As a cart goes down the ramp, the total amount of energy here has to equal the amount of energy here. This idea is known as conservation of energy. And is based on the concept of giving something potential energy. In fact, the energy here at point 1 is the same as the energy here at point 2 and the energy here at point 3. In fact, at 3, does the object have very much potential energy? No, it's very close to where it started, which means almost all that energy is now kinetic. Can you agree that it's probably going fastest at 3 compared to 1 and 2? Over here at 4, it's probably going a little bit faster than it was at 3 because it's not as, faster than it was at 3 because it's no longer at the bottom. It's probably going a little faster than it was at 2 as well, right? Would you agree? Because it's not as high as it was when it was at 2. The thing about conservation of energy is you can just set these two things equal to each other. You can set the energy equal to any point in the ride. Now, this part, I don't know if you'll catch on because we only have a minute left, but did you notice that all I really need to know is how high this is? In fact, did you notice that every single time we calculated the change in gravitational, or the work done by gravity, the work done by gravity was always the force of gravity times whatever the height was? Did you guys notice that? We will define gravitational potential energy based on that idea. We'll say that gravitational potential energy is mg, the force of gravity, times the change in the height. we'll say that the potential energy is equal to the force of gravity times the change in the height. This is actually quite a big deal because of what it means for our problems tomorrow. You're going to find that we can do stuff we could never do before, but you're also going to find that conservation of energy problems are probably the easiest kinds of problems there are. There are two forms of potential energy. Well, that'll wait till